Okay, today we gonna continue lecture 9. We started last time and we talk about second law of thermodynamics. So we have a good shot there and we're almost done. Let's take in the first 30 minutes to finish lecture 9. Then we're gonna talk about lecture 10. So today, as you notice, that today is the first day of our fifth week. So today officially it's lecture 10 and today it's second or 20. So I will discuss why it's out. W net can be dot. Everything can be dot. And this is power plant. Power plant, it has 4 components. We discussed them last time. For example, power plant, it has pump. It has combustion chamber or boiler. It has turbine that expand the flow. It has condenser. Go back to pump. Let's say pump, boiler, turbine, and here we have, for example, condenser. Even this turbine, it drives a generator. Then we take here W, for example, dot electricity. We're going to discuss this right now. So this is the first plant diagram. This is the first plant diagram for power plant or heat engines in general. We have another thing which is called refrigerator. Unlike heat engines or power plant, refrigerator, Q low is the desired. So we have W dot, or for example, everything not net in. This is Q high, which is output also. This is the desired, and this is the input. But this plus this equal this. This equal this plus this. So always Q low plus W net equal Q high. Q low plus W net equal Q high. The same for heat pump. There is something called heat pump. So what's the difference between this and this and this? The difference is what is input, what is output. For example, the heat pump or heat engine generally, I want this. I pay. This is the input. This is what I want, desired. For refrigerator, I pay this. So I want this. I want Q low. This is input. This is a system. This is a system. This is a system. For heat pump, exactly look like refrigerator. Q low, Q low. W dot in, W dot in. Q high, Q high. So Q high is out like this. But here in refrigerator, like fridge, we have desired. We want everything in the refrigerator to be cooled down. So we want Q low. Here we want Q high. Like something like boiler. Something I want heat in water warm in the bathroom. So our input is work. So I pay here electricity to get Q low. I pay electricity to get Q high. Here we use eta thermal, which is, for example, W output over input. Everything is output over here or here or here. Output over input, output over input, output over input. Here W net out divided by Q high. Sometimes Q high is M dot heating value, what I paid. This is eta thermal. For this power plant, this is a thermal efficiency. Thermal efficiency. Thermal efficiency. For here and there, we talk about COP, coefficient, both of them, of performance. COP. COP, refrigerator, REF, and you have COP, heat pump. Always output over input, output over input. Here we simplify, for example, 1 minus Q low over Q high, if you remember last time. COP refrigerator, it's output over input. COP over heat pump, for example, it's output over input. So here simply it's Q low over W net in. Heat pump, nope. The output, what I want is Q high. I want warm water, W net in. Of course, you can dot for everyone. If this is per unit time, so this is dot, it's okay. You can say, for example, COP heat pump equal COP refrigerator plus 1. So Q high is W net in plus Q low. W net in over W net in is 1 plus Q low over it, which is COP refrigerator. This is a simple division. So you can say COP heat pump is COP refrigerator plus 1. Always everything is more than 1, but this is always more than 0. It is always less than 1, of course. Thermal efficiency. This greater than 0, but it can be greater than 1. It can be greater than 1, no problem. It's all, everything is greater than, it can be greater than 1, but it's always greater than 0. This one should be greater than 1. This is only one, it's greater than 1. COP heat pump. It's 1 plus. It can be half, it can be 1, it can be 2. This can be 1.1, can be 1, that means 0 efficiency. It can be 1.5, 3, 4. The bigger, the better. I got too much Q high from work in. Okay, guys, any questions? Any question, guys?
Professor, what does it say on the power plant diagram? The last branch that is sticking out? I'm not too sure what it says.
So here?
No, the one that has the, yes, but on
So
the
we
top.
have, this is turbine, generator. This is generator. And this is turbine. This is electricity, power electricity. We're going to discuss about this right now. This is a condenser. This is pump. This is boiler. This is turbine. Anything else?
Professor, what does this say on the by COP-HP on the other side? You put CO at the end of the equation. You put
It's C
COP.
of refrigerator plus 1. If you want to drive it, it's so simple. This one is Q low plus W net in, correct? Always this plus this equal this, always. This plus this equal this. This equal this plus this, always Q low plus W net out or in equal Q high. Okay? So Q high is equal to this plus this. When you divide this by W net in, it means 1 plus Q low over 1 over this. This over this means 1. This over this, it means COP refrigerator. So this guy equal COP refrigerator plus 1. Make sense?
Yeah, thank you.
No worries. So in the exam, I will ask you, for example, derive this from this, this, and this. We're going to go back and forth between them. And when we add T low over T high, we're going to add them to them. We're going to discuss it in Carnot cycle by the end of the following lecture. So what happened? We have heat engine. We want work. I will explain this now in details. We want work. I want to pay some fuel. Here I'm paying HVQ heat value, M dot fuel or M fuel times heating value. I'm paying fuel, kerosene. I'm paying fossil fuel, even some nuclear power to get work. to have electricity finally, to have mechanical work that drives the generator. Then I dump the waste. Second law says you cannot have this. You need to have this. If you don't have it, you don't have cycle. If you have a cycle that operates and you have one single reservoir, you cannot have one network. From where? Kelvin Planck statement. So you need to have always two reservoirs, Q high and Q low. One source, one sink. Some of energy are not useful. But if you have Q low is 0, which is impossible, you have 100% efficiency. Of course, if you want to talk about percentage, you can times 100% if you want. The same for refrigerator, but the opposite. Here, Q high input, the work is output, and Q low is output. Here, the work is input, the Q low is input, and this in the cycle. But what I want this, I want everything in the refrigerator to be cooled down, temperature lower than ambient. So I pay some electricity, to obtain this. Then the heat, I dump it in the ambient. The heat, I dump it in the ambient, like in our home. We have a refrigerator, always in the back, it's hot. This is the Q high of refrigerator. The same for heat pump, but heat pump is different. Heat pump is something I want to heat, different from heat engine. Heat engine, we want work. Heat pump, I want heat. I want to heat up the water. I pay electricity to get heat. I pay electricity, and this is the waste. So the water is cold. This is kind of waste. I pay electricity to make it warm. The water is cold. Pay electricity, became it warm. Water is cold. Pay electricity, became warm. Here, everything is hot. Put in the fridge. Take heat, dump it in the air. Take heat, dump it in the air. Here, I pay heat to get mechanical work. Is it easy, guys? Is it easy or hard, guys?
It's okay.
It's okay. Yes and no, man. Thank you. So we have here power plant, refrigerator, and heat pump. We measure them was thermal efficiency, output over input, COP, coefficient of performance for these two, which is output over input, output over input. But my output in refrigerator, Q low. My output in heat pump, Q high. So you need to always ask yourself, what is the desired? What do you want? What do you pay? Here and there, I pay electricity, W work in. That's what I pay. Here, I pay heat. That's what I pay. And that's what I get finally. So you need to ask yourself, what is the output? What is the input? Different from power plant, refrigerator, and heat pump, they are different. The last two, refrigerator and heat pump, they have coefficient of performance. Sometimes they are greater than 1. The first one is thermal efficiency. Let's talk about important efficiencies. Let's talk about this one. I'm gonna focus now for a few minutes in the power plant. We're gonna go back to this guy and this guy later, even with detailed problem. Now today we're gonna talk about detailed problem. You're gonna see actual refrigerator, and we're gonna get some states, and we're gonna calculate COP. For here we got efficiencies. Any efficiency, guys, any efficiency, any efficiency it's output over input. Do you remember when I talk about any specific, something specific, it's something over mass? So efficiency is output over input, okay? So let's talk about, for example, the boiler. The boiler. We have here, for example, Q high, Q out, and we pay M dot HV. So we pay this, and we get Q high. Sometimes when you put fuel inside the boiler, not everything burned. So you have efficiency, which is eta, let's say boiler, or eta combustion chamber, the room that we burn the fuel in. equal output over input. What is the output? Q out. What is the input? This. So it's Q out, which is the output from the boiler or combustion chamber, over input, which is M dot HV, if this is dot, for example. Let's talk about turbine. Turbine, it has here W net out. So eta turbine, it's output over input. What is output? Mechanical work. What is the input? Some heat. So the output is W net out. Divide by Q out. We have here generator, eta generator. It's output over input. Output, which is W electricity over W net. So W electricity, which is output over W net. So the output, the input to the generator was W net out from the turbine. The output from generator was W electricity. So what about the thermal efficiency of power plant? The thermal efficiency of power plant, I'm talking about now details. So the power plant, which is everything. Let's say we'll talk about everything here. What is the output? What is the input? So eta power plant, it's output over input. Output, which is W electricity, divided by Q, actually M dot fuel HV. Correct? It's W electricity over this. Output over input. Output over input. If you want rate. If you don't want rate, remove the dot. It's okay. Both are correct. Power plant, output over input. So if I add this guy again, let's say I add W net out, W net out. I did nothing wrong. If I add W net out, division and multiplication, it's okay. The same for Q out. If I add Q out, let me another color. For example, Q out, Q out. Guys, what is this? What is this? Eta generator. What is this? Eta turbine. What is this? Eta combustion chamber or boiler. So the eta power plant is generator efficiency times efficiency of turbine. It's getting smaller. Let's say 80 or 95%, 85%, 50%, 80%. Multiplication of those give you a very smaller efficiency. The product of all efficiencies in the system. Efficiency of this, time efficiency of this, time efficiency of this, give you efficiency of the power plant. Power plant. Okay? Boiler efficiency, output over input. Turbine efficiency, output over input. Generator efficiency, output over input. If you multiply this by this by this, this cancels this. This cancels this. It became output over input. Make sense, guys? Does it make sense, guys?
Yeah.
Are you still alive, all of you? Does any one of you not happy in his life, in general? In the midterm?
Oh, we're happy, man.
Oh, dude, thank you. What should I do? I don't know. Okay. How about the midterm? You were happy from the midterms? Midterm was fine?
Yeah.
It was cool.
Does any one of you think any problem in the midterm was not kind of implicitly given in the lecture or the homeworks? Anyone think it's not given similar or the same? Something like big. What is this?
What we saw in the
I
lectures.
think, yeah, I think what you saw in the mid homeworks lecture, it was kind of given, maybe not exactly directly the same problem, but very similar. So from now on, if you solve the homeworks yourself, you're gonna be so happy. If you solve every problem in the lecture, you're gonna be very happy. Please open with me lecture 9, page 7, or in the book, problem 618. I think when I post the lectures, I put for you from chapter 1 to chapter 6. If any one of you want the list of the chapter, please email me. I'm gonna email him chapter 7 to chapter 11 if you are interested in. You know, it's illegal to upload everything from the book online. I'm supposed to give you chapter or 2 or maybe 3, but I give you 6 chapters until you buy the book. But anyway, if you want some more chapters, let me know. I can send you some chapters, okay?
Thanks, Professor.
No worries. So now, please read problem 618. I'm gonna now go deep dive in problems. The good news is the problems here are so easy. Much easier than chapter 1 and 2. It's a little bit from chapter 2 for homework 2, a little bit. But it's much easier. You will see that. You will see, oh, that's easy. That's super easy. 2 equations or something, and that's it. Or maybe 3 with COPs. So if you remember always output over input, you will have a beautiful life. COP or efficiency, it's output over input. That's simple. 618. So the first thing you need to recognize is, what is this? We have heat engine or power plant. It has thermal efficiency. We have refrigerator and we have heat pump. This has COP refrigerator. This has COP heat pump. Always remember which one you have. The Venn diagram here different from there. They are very similar. The Venn diagram is the same here between this and this. The arrow is just opposite of here. So when I ask you to plot the Venn diagram, remember to plot it carefully, correctly. So problem 618, we're still in chapter, problem 618, we're still in section 6.4. We have heat engine. I give you thermal efficiency, which is 0.85. That's very big. I think 0.35. And we have work in, actually out, this is out, was 60 horsepower. He want Q in. That's required. And this is heat engine. It's not heat pump, it's heat engine or power plant. So the solution is so simple. So simple. We have 2 inputs, that's easy. As I told you before, we have only 2 equations. Q high equal Q low plus or input plus W net out. The same equation for this and this and this. Efficiency, which is either W net out over Q high or 1 minus Q low over Q high. That's it. So as far as of now. Next lecture, we're going to add a little bit more things, but this is out of now. So you have now, this is kind of Q low, or actually Q high. Input is Q high. So you have this. Oops, let me also clarify. You have this and this. Can I get this, guys? W net over eta thermal. Is it hard, guys? 127.8 kilojoule per second. Yeah, we convert horsepower. If you want to convert this, multiply 7 for, I think, 5 kilojoule or joule. This is joule now over if you make it times this time, divide by horsepower. So this is became this time this give you how many joules? 0.745. It means joules. So this multiplied by that. Of course, this is hour. This is horsepower. It per hour. So we have here, I think 60 seconds, 3,600 seconds. Okay. Okay. Because kilojoule. Okay. Just the output is here. Either divide this over thermal efficiency, you got in horsepower, or divide this, multiply by this. So it's gonna be 127.84 kilojoule per second, or kilowatt. That's it. Okay, guys?
Professor, what's that value right next to the 60 horsepower? You said that's the conversion, right?
Yeah, if you want to convert it back to joule, multiply by this number. If you want to keep it horsepower, it's okay, as long as I did not ask for changing unit. But if I ask you to convert it back to like 1 horsepower, equal 7.4, I think. So I think 743, because my phone number is the last 4 digit. It's kind of this. That's why I remember it. So this is joule per second. So this is the conversion from 743 or 7. I think 5 or 3. I don't remember. So one of these. Okay, guys. Or 6. I think you can make it 6. 6 is better. Yeah. Okay, guys. So the horsepower equal this. So you can remove this by putting this here. 6 times this give you how many joules? If we divide by 1,000, it became kilojoule. That's what in the exam. That's why. So kilojoule per second with kilowatt. This also can be kilowatt if you want. So here, this is the final output in kilowatt. 127 kilowatt with 35%. This is actually not bad efficiency. This is kind of good. Let's say you imagine you are paying 100 watt, you only get 35 watt. So this means you are paying 100 watt, you get only 35 watt output from this heat engines. This is a kind of typical value, 40%, 20, some engines 20% only thermal efficiencies. Okay, guys? The same problem 22nd, 22. You have also, if you go to the next page, problem 622. In chapter 6, problem 22. Read it. It's the very same. Except instead of giving you Q high, I give you Q m dot and heating value. So I'm gonna 22. I give you m dot and heating value. With those, you can get Q high, which is just m dot fuel times heating value. It's 30,000 kilojoule, because I told you about this before. This is for every fuel, we have heating value. How much joules I can get from this fuel per kilogram. If I burn 1 kilogram of certain fuel, or even like liquid or solid, I can get some energy. Like for example, for kerosene, for coil, this number. Multiply by how much mass you burn, rate, give you Q high dot, for example. And I give you W dot net out. I give it to you also. If you divide this by this, you can get thermal efficiency. Output over input. It was 150 megawatt. So we can keep even the same problem. Everything to keep the same. Like this. The solution is the same. What we want required? Eta thermal efficiency. So we don't want this now. Actually, we can use it, but we don't want it now. We don't want this part. So it's eta thermal. W net over Q high. Q high is m dot heating value. So we can do it this way. Eta thermal is W dot net out, which I have it, 150 megawatt It's a very huge power plant divided by Q high, which is m dot fuel times heating value, which is HV. It's a coal power plant. We can get thermal efficiency. Of course, you're an engineer. When you get thermal efficiency, try to make sure that makes sense. If you calculate this thermal efficiency, problem 22nd, it was 30%. That's typical value, like 0.3. You're gonna find it 0.3 as an issue. Then you're gonna say this is 30% efficiency, thermal efficiency. Okay, guys, make sense?
Yep.
Now, problem 26. Please read problem 626. Read it. When I say read it, means read it because in the exam you will read it yourself. From now, you need to read it. Hey guys, did you read problem 26? Please guys, do not email me or send me any late homework, quiz, anything. I'm not gonna accept anything late from now on. Actually, I don't use to do that. So do not send any homework by any reason, okay? You have 1 week to submit it anytime. So please do not submit anything late, please. I'm gonna discard the email or even the submission. Okay, 26. 26, the given for you was it's a power plant, and I give you the work net out, which is output, of course, from this, a 300 megawatt, a big power plant, kind of big, with thermal efficiency 32%, 0.32. Air to fuel ratio, which is m dot air over m dot fuel, or m air over m fuel, equal 12. So as you know, we have 3 things to have successful combustion. We have fuel, we have oxidizer, like air, we have the ignition. So air to fuel ratio, something so important in engines, is called air to fuel ratio. M dot air over m dot fuel is given here. Heating value was 28,000 kilojoule per kilogram. So for every kilogram of this fuel, I can get 28,000 kilojoule. Required. A. He said, in 1 day, in 24 hours, how much coal did you burn? How much fuel did you burn? B. How much air? M dot air. Again, you have this and forget about this now. This and this, you can get Q high. Heat thermal output over input, which is Q high. You can get Q high. Q high is M dot fuel times this. You can get M dot fuel. M dot fuel and M dot air, you can get how much M dot air and how much coal. So the solution is so simple. Solution. Heat thermal equal output over input, which is output input in this power plant is m dot fuel times heating value. As I always tell my students, look at the equation. You have this, you have this, you have this, you can get that. That's it. If you have one unknown per equation, you are fine, you are great. m dot fuel equal w dot net out divided by eta thermal times heating value, which is how much fuel we can burn in this engine. It was 33.48 kilogram per second. Every second I burn almost 33 kilogram, almost 0.5 kilogram of this fuel. This is m dot. Make sure everything in SI. So for example, this guy megawatt is 10 to the 6 watt. That's fine. This is just 0.32. This is correct. Kilojoule. Oh, this is 1000 joule. Make sure everything is SI. Mega is 10 to the 6 watt. Efficiency 0.32. Heating value is 1000 joule for kilojoule. Kilogram is kilogram. Kilogram is an SI unit. It's an SI unit. Kilogram. Kilogram, meter, second, Kelvin. Make sense, guys? So far, no problem. Do you have any problem? Have any problem, guys? Guys?
No, we're good.
M dot is mass over time. If I want mass, it's just M dot times time. That's it. If I want this per 1 day, multiply M dot times 1 day of time here per second. This became in second. You can get the mass in 1 day. So M dot means mass per time. Assuming you always, every second, you put 33.5 almost kilogram. After 3,600 seconds times 24, you can obtain this. So it's M dot times 1 day, 24 times 60 times 60. 24 hours, 60 minutes, 60 seconds. So you can obtain how much kilograms you want for this fuel. Not M dot, it's M, mass. It was 2.89, 10 to the 6. Oh, wow. Almost 3,000 tons. Almost 3,000 tons daily. M dot air. M dot air, because we have this. Air to fuel ratio. It's air to fuel, AF. M dot air divided by M dot fuel. So we have this 12. We have this 33.48 or 5. So you can get how much M dot air. M dot air, it's air to fuel ratio times M dot fuel, which means 33 times 12 is 401.8 kilogram per second. Every second I want almost 400 kilogram air. Remember, every 1 cube meter, almost 1 kilogram of air. So if you have 1 meter, the density of air is almost 1. So every 1 meter by 1 meter by 1 meter cube, it's almost 1 kilogram of air. So you want 400 kilogram of air to burn this fuel. That's actually so bad. This engine is so bad because it's a lot of pollution, a lot of mass to obtain just 300 megawatt. So if you don't know, actually my PhD is mechanical and nuclear. That's why I am aware of nuclear power. So if you want to obtain the same power like this, what?
I said that's pretty cool, man.
Yeah. Okay, thank you. So in my degree, I need to take some courses in nuclear. So if you want to obtain this power from nuclear, like uranium 293, so you can only use few grams. Every 1 gram of uranium equivalent to almost 200 tons of coal. Almost 1 gram. Imagine how big it is. So if you want to obtain this power, you may use few grams, maybe 10 to the 6, maybe about 2 or 3 grams, maybe, of uranium. About. I think so, yeah. So imagine how big it is. Of course, if using in civil, not bomb. I'm talking about the good use of nuclear. Okay, guys. And you can obtain the same, exactly the same. Okay, we are done now, almost from chapter of lecture 9. Let's go now dive and check. Again, in chapter 10, lecture 10, we have the same thing, some problems in the very beginning. And let's take one problem is good, which is refrigerator 143E. That's a very good problem for you to mix between the first chapters and this. I think like 2 or 3 grams here can be equivalent. With losses, you can say 5 grams. Because in power plant of nuclear, you have a lot of cooling, a lot. The control rod, it needs to be cooled always. So you may use maybe double or triple this number. So at most 10 grams, I believe, to obtain the same power of 100 megawatt per second, 300 megawatt per second. Anyway, so the problem for you was 55, 655. If could please read problem 55. Problem 5655 in the textbook, or page 10, page 10, 2 in your lectures. Lecture 10, page 2. Please read problem 655 in your textbook. You will see a similar problem in the final midterm 2. Guys, this problem is refrigerator or heat pump? Guys,
Refrigerator?
It's heat pump, no?
exactly, heat pump. Refrigerant fluid, but this is heat pump. Read it again, guys. No, that's refrigerator. Oh. 1 minute. It's refrigerator or heat pump? What was it, guys? 1 second. I'll go back to the lecture because I don't have the notes here. because I wrote it different time, 2 times differently. 1 second. Let's get courses. Thermodynamics. Yeah. So problem 655. Oops. Did you read, guys? Heat pump. Okay, guys? Can you see the second line? Heat pump. Can you see it, guys? Refrigerant fluid 134A enters the condenser of a residential heat pump HP at 800 kilopascal. So this is the entrance. I actually plot for you condenser, and it enters with 800 kilopascal and 35 Celsius at a rate of, this is a mass flow rate, and leaves at, it gives you saturated liquid. It means X equals 0. So I give you before, let me share with you the screen. I think would be better. Guys, do you have any questions? So here, this is heat pump. Give you the input before the condenser, temperature and pressure. It means I have total all the information at this state. I have also the output. I have 2 independent intensive properties. Give you. It leaves at this as this. Saturated liquid means what? Means 0 quality. There is no vapor. X equals 0. If the compressor contains power, so this is a W dot N. Find the COP of heat pump. COP heat pump, and rate of heat absorption. It's Q low. So I want Q high, Q low, and have this. Okay, guys. Okay. So what happened? He gave you W dot not N. Give it you. If I have efficiency, for example, or COP, I can get Q high. But unfortunately, he did not give you anything else. But he gave the state before and the state after. What should I do if I have a state before or after? I use first law of thermodynamics for open system to get the Q high. So let's go back here. So he gave you state 1. So this is a heat pump. Heat pump. Use refrigerant. The fluid moving in this component, refrigerant. We have Q low. We have W dot net in. We have Q low dot, for example. We have Q high or Q high dot. He wants COP heat pump. He wants Q low. Unfortunately, I only have this. I only have one thing. I said to you before, we need 2 things. This COP or one of the heats, I can get everything else. But he gave you everything here and everything here. From these 2 states across one component, I can use first law of thermodynamics to obtain the heat here. So Q high or Q12 minus W12. I don't know, remember, M dot, this is steady, that's M dot constant. H plus V squared over 2, but there is no even kinetic energy, minus H2, 1. So equals 0. It means there is no work here. This is condenser. So the change in enthalpy, drop in enthalpy, reflected in Q high. So this is Q high. M dot, we have it. State 1, we have it. State 2, we have it. We have state 1, we have state 2. We can get Q high. If it's dot, so M dot, H2 or H1 minus H2. Okay, guys, H1 is bigger because this go other side would be negative. So H1 minus H2. H1 high energy go to low energy because I dump some energy outside. 1 equal this plus this. You can say it many ways. Okay, guys? Okay, guys? Guys, can somebody tell me how can I get H1? Which table? H1. Yeah, P1 and T1. This is R134A. We have here P2 and X2. Guys, are you here? Guys, are you here? Hello?
Yeah.
Can you tell me how can I get H1 from which table? Go to the steam table, open the first page, you will see the tables.
Is it A13?
Exactly, 1, 13, 14, 15. This guy is superheated. The first state one, superheated. It means table, the last one, 14. Okay, guys, A14. Oh, actually 13, 13. 13 is the superheated one. 11, 12, 13. So 13. 13 exactly the superheated. This is A13. Table A13. You can obtain H1. What I want here, H1. Then here, X2 equals 0 and P2 we want it. We have it. So we want H2. From where, guys? What table? Can somebody tell me? H2. What table? Saturated liquid. Refrigerant 134A. Where is the table? So the first one, we want that superheated. Yes, that's the table A13. So which one, the other one? You have pressure and you're looking for saturated mixture or at saturated liquid.
Is it 12?
A12, exactly. A12. This is a pressure base for saturated mixture. So when you go to table A12, what variables you gonna take? Because quality is 0, what variables? Subscription F, subscript F, or subscript G? Liquid or gas?
Liquid.
Which is F. Perfect. So liquid is subscript F. So when you go to this table A12, for example, let's go to A12, refrigerant 134A, pressure base or pressure input. This is A11. Nope. We want A12. Here, this is A12. The first symbol always F, VF, UF, HF here, HF, this one. I want this guy. At certain pressure, whatever pressure I have, this pressure, I can go and get my, what the pressure was, the pressure to HP2, 800. So go down 800, it's here, 800, here, at HF, this guy, 85.48. Because X equals 0. If you have X, you need to use HF and HFG, which is H equal HF plus X HFG, but X equals 0. That's why we don't have HFG, this guy. So we only use the 85, which is H2. Okay, guys, make sense? I've done this many times. So for refrigerant, we get H1 and H2. You can easily get Q high. So you have H1, state 1, state 1. This at state 2. You can get H1 and H2. You can get Q high. So once you get Q high and you have work output, you can get anything else. COP, Q low, anything else he wants, you can obtain. Q high was 3.16 kilowatt. 3.16 kilowatt. Definitely Q high must be greater than work. The work was 1.2 kilowatt. This is 1.2 kilowatt, 3.1. So remember, guys, this plus this equal that. Q low plus W dot not N, it's equal to Q high. Q high must be greater than everything else. Heat pump, refrigerator, power plant, anything. Q high must be bigger than anything else. So this is good check for you. And of course, it's negative. Why it's negative, guys? Why is negative?
It's heat going out.
Perfect, exactly. We said heat addition positive, heat rejected, it's negative. That's why it's negative. We don't care in equation to be positive or negative, but we know what's going on in our equation. If you want COP, COP is output over input. It's always, everything is output over input. What is the output here, guys? What I want from heat pump. What I want. Q high. What I paid for? What I paid? W net in. So I pay some electricity, I pay some power to get heat. That's called heat pump. I pay some electricity, some power to get heat. So it's 2.6 COP. So once you get this and this, it's 2.6. Correct? Yes. 2.6, almost 2.5. Okay, let's take 4 or 5 minutes break. Clausewitz gave a statement about second law of thermodynamics. We have taken before Kelvin Blank. They said it's impossible to have a device that operates in a cycle and it takes heat or so from single reservoir and produces net work. It's impossible. It's impossible. You cannot have this. For example, you cannot have this. This is a Kelvin Planck statement. You cannot have this. Q high, and this is cycle device. Any device, and W. You cannot. Some energies are non-useful. You need to have the last part. This is impossible. This is impossible. This is what Kelvin Blank. Clausewitz gave a similar statement, but a little bit different. Clausewitz. So in 6.5, in the very end, second law, Clausewitz statement. Again, this is the researcher, this scientist gave his opinion about second law of thermodynamics. He said, it's impossible. I'm writing this, guys, because I'm not going to ask you directly, but I'm going to ask you who said that and how he said it. So you need to know what's going on. To build or construct a device that operates. Hello? Guys, if you are not using the mic, please turn it off because they get noise. Okay? Write it down now. I'm going to check it. So what he said it's impossible to construct a device that operates in a cycle. Produces no effect other than transfer heat from high temperature body to low temperature body. I think this is high to low. So what happened? He said that you have Q high and you had a cycle. A cycle must be a cycle device. You have kilo. This is impossible. You're supposed to have W net out. So it's very similar to this guy. He said you cannot have a single reservoir. He said you cannot have two reservoirs, one high, one low, and you don't have no effect other than you cannot have this. So remember this chart for Kevin Blank. Remember this one for Clausius. Okay, guys? That will drive us. So these guys are very good, very good. Clausius is a very good scientist. He had a lot of theories. And this is so important. You know why? Because this also somehow related to the first law of thermodynamics. The energy cannot be neither destroyed or created, nor created. So of course you cannot have high energy, just dump it in low energy. That's it. It's simple. If it's a cycle, it means it go to initial state. But if it's not cycle, yes. If it's, you need to make sure that you understand what is given. So it's impossible to have a cycle device operate between two reservoirs without any effect other than this heat. Okay, guys? Okay, guys?
Yep.
So these kind of statements and discussions are important. And usually, if you end of the next lecture, you will see, next lecture, lecture 11, you will see a lot of derivations in terms of problem derivation. Like I give you problem, prove for me Clausius statement. Prove me, start from Clausius statement, go to Kevin Blank. Start from Kevin Blank, go to Clausius. So you need to understand them. So if you start from this, you cannot do that. If you start with that, so if this is correct, this is correct. If this is correct, this is correct. Kevin Blank. And so in section 6.6, we have reversible and irreversible processes. What is this? I think you have heard this before, but let's talk about it. Reversible and irreversible process. Let's talk about reversible process. Reversible process. A process that can reverse with no influence on surrounding. So let's take an example, guys, of this interesting thing. Okay, let's say I'm gonna, usually I took strange examples, but they are real. They are very real. They are very good for you. So let's take an example. Let's say somebody give you $100 for a loan, for example, and after a few weeks, you give it back to him, $100. Okay, this is called reversible process. You took money, you get the same money. No one get hurt. Nothing changed. Correct? But let's say somebody was bad, like the bank interest. So I give you $100. I said, after 1 month, give me back this $100 and $102, $103. Every month at 3%, 2%. That's because I'm Muslim, I usually, that's no interest. So that's no way to have it. So even anyway, so this is, for example, wrong because this is irreversible. This is, it cannot be happen. If you have $100, return it more, it's impossible. This is not irreversible because you return it more. So that has influence on the surrounding. Let's talk about a heat transfer problem. Take another heat transfer problem. Let's say you have a piston cylinder like this, and you have trapped a gas, and you add some power to compress this gas. Nicely, you compress it. It goes from here, let's say, to there, a little bit compressed. This is compressed gas. What happened? If I left this guy, left the force, and it turned back, I supposed to take the same power I paid. Let's say I pay here 100 watt. I supposed to get back 100 watt. If I get back 100 watt and this back, return back to original position, that's a reversible process. But what happened in reality? This gas get warmer. Some heat escape, some friction happen here. So you're gonna get about 85 or something watt. That's called irreversible. You cannot go back to the same place and the process totally reverse it. You can reverse it. Like how come the here? Reverse. This is should be reverse. Can reverse with no influence on surrounding. But if you reverse it, you have already have friction. You have heat. You have warm gas. This kind of all losses. It's impossible to go back to original position and get the 100 watt. But if you want to make sure there is zero friction here, there is no constrained gas here problem, so you will of course get the 100 watt back. Okay, guys, you know what is reversible is. So in reality, everything is irreversible. In terms, if you have friction, if you have zero friction, of course you have this. So you have some friction, some compressed gas. So you have irreversible process. Irreversible process, which means no reversibility, like friction. This is a very famous thing in reversibility. So let's talk about second law. Second law, the efficiency. Actually, second law efficiency, we're gonna talk it back. Eta, we're gonna talk about later. But this is talk about better design, best design. The more you have this, the better it is. It's called second law efficiency. It compares the performance of different devices. This will be much better if you have reversible process. The more you reversible, the better you are. The more you reversible, the better this efficiency is. So we wish to have designs that they are reversible. They are reversible. The reversible is the best efficiency ever, and we're going to talk about it in details later. So what causes irreversibility? We have something called irreversibility. What it causes this? There are three like famous things, like friction, like this problem. Whenever you have friction, you have problem. Whenever you have restriction, you have problem. You have heat transfer. This is always cause problem. Heat transfer. If you have a cup and you heat it up, heat transfer. Usually it's irreversible. Why? If you heat up, if you add here 100 watt, of course the ambient, the surrounding air will get a little bit of this. Let's say 30 or 20 joule watt. If you want to go back, can you get the heat from the air? Put it back here in the fuel here? Impossible. This is gone. 30% or even more of the heat gone into ambient when you warm up something in the oven. So this is no way. Whenever you have heat transfer, of course you have irreversibility. Okay? Irreversibility. It means you always have something. You cannot go back to original place and getting what you paid from originally. So you go from A to B and you do something. You cannot go back to this and get the same thing you paid for. Let's pay 100 here, got 80 here. That's called irreversible. Irreversible. The last one is unconstrained gases. Usually in our problems, we have gas constraint. These gases causes irreversibility, like this piston cylinder. If you have any leak, sometimes even not even leak, just due to compression or expansion of the gas, you may have irreversibility. You cannot go back. It's called unconstrained or unrestrained. What? What? You have a question, guys? Guys?
I think his mic's on accident.
Okay, no problem. So this is 6.6. 6.6, the conclusion is some things are reversible, yes. Some things are irreversible, yes. But most of the things are irreversible. We wish everything is reversible. This is called ideal life. This is more reality, but we have some irreversible processes, but they are very limited, very small, and you have almost no friction. Almost. This is more real. That we have some losses, unfortunately, and we wish there is no losses. Like, let's take back to the bank and about the interest. When crisis happen, like this crisis, for example, the pandemic of COVID and COVID-19, what happened? The banks reduces the interest rate to almost zero and negative in some of them. One of them, by the way, almost zero and negative, because there is no problem. There is a major problem. There is no money. So you need to go back to the ideal. If you put money, you're not going to get anything. You need to take your money and pump it into the economy. Okay? Okay, guys?
Professor, what's a real example of a reversible process?
Okay, if you have the same problem here and you have zero friction, if you have really zero friction, for example, argon is an ideal gas. You know argon?
Yeah.
This is PV equal RT. 100 Z equal 1. No way. This is, if you compressed it, it has zero friction. Because this gas has no constraint. If you compress it, whatever pressure you pay, you can get what instead. So if you compress it and leave it, it's going to go back exactly. But to obtain this, you need to have, for example, temperature, I think, minus 180 Celsius. That's a very low temperature. Even does not exist in reality. You need to have a design for that. That's a very low temperature, a very low one, to have to go to the liquid gas, liquid fluid of argon. Okay? Okay?
Yeah.
So this in gas form, which is our here, this always valid because argon is an ideal gas. But you need to go a little bit lower to have more ideality. Until 9 minus 180, that's the liquid. You need to be a little bit above it, of course, because it's gas. But it's always the equal one. You have perfect gas, no restrained. Actually, we used to use restrained. Restrained gas, no unrestrained gas. You can have zero friction. It's ideal gas. Zero friction. Ideal means there is inviscid flow, inviscid, zero viscosity. In reality, we have viscous fluid like air, even vapor. 6.7, that's a very important section. It's called Carnot cycle. Carnot cycle. Okay, Carnot cycle is the first cycle in life. It's a very ideal cycle. The most important cycle. However, it's very ideal, but it's very important because this is the upper limit of maximum efficiency. So you cannot obtain efficiency more than Carnot. If Carnot said the efficiency 70%, this is the maximum efficiency. If Carnot said the maximum efficiency is 80%, this is the maximum. You cannot get 81. It's impossible. If Carnot said this efficiency is 75, you have 75, 60%, 60%. And this is the typical range, 60, 55, 70. 70 is big. So what Carnot said? Carnot gave a cycle, piston cylinder. Piston cylinder is a typical good process because there is no, you can make it isolated. There is no heat, or you can only take some heat if you want, control. But you cannot prevent, you can prevent heat from escaping. You can put unconstrained gas inside, unrestrained gas, or incompressible fluid. Let's plot it from, one. One is kind of here. Let's say this is the fluid. Gas, here, gas is good. And we have here a piston. This is state one. This is the control volume. This is gas. Let's say state one. And I'm gonna change it. I'm gonna expand it. Then I'm gonna compress it. Then I'm gonna expand it again. I'm gonna draw it later. So this is 2. So for 1 to 2, this is a Carnot cycle steps. I'm gonna say it again in details, but follow me. It's a reversible, isothermal, expansion. I have gas here. I want to expand it. Reversibly, there is no heat added. Reversible, Q is 0. Isothermal, temperature is constant. Temperature start at 50 degrees, remain 50 degrees. This is state 2. State 2, temperature is the same as here, isothermal. Expansion, the pressure here was smaller here because expanded. Volume became bigger, pressure dropped. Here was what atmosphere? Half atmosphere. From 2 to 3, actually, let me draw it differently because we have also expansion here. Okay, no. So the first expansion was isothermal. He said, no, I'm gonna do another expansion. 2 to 3, another, we call it reversible adiabatic expansion. So this is just reversible. Reversible means it has 0 irreversibility. I can return it back. I will see that later. So this is reversible adiabatic expansion. It means Q equals 0. So here I can add Q, but this Q is kind of controlled. I can take it back, turn it back to original position. So it moves, but I add Q. Then here what happened? So it's gonna go back again, gonna more expansion. But adiabatically. I left it, it expand. 3 to 4, now this is compression. Reversible, isothermal, compression. So we have, it's gonna go back something similar to this one. So from 4 to 1, gonna go back to 1, exactly like 1. We're gonna mix 4 to 1, which is reversible, adiabatic, compression. 2 expansions, 2 compression. Reversible, isothermal, reversible adiabatic. Reversible isothermal, reversible adiabatic. You see, kind of 2 expansions, 2 compression. Let's plot them in PV diagram. PV diagram is good. Here, PV diagram. Let's plot them in actually also TV diagram. So in PV diagram, we have constant temperature line. This is gases. This is called T equal constant. T equal constant. Look at this, guys. T1 equal T2 and T3 equal T4. We're gonna kill T1 and T2. For example, T high. T high. Then we're gonna call the other two T low. So we have here 1. We have, I'm gonna explain that now. 2, 1 to 2, reversible isothermal. Temperature is the same. If you remember, if you want to remember, guys, if you go back to the PV diagram, PV diagram, we have constant temperature line. You remember this, guys? You remember this, guys?
Yeah.
This is called constant temperature lines in PV diagram. They're getting diverging, decreasing. This is temperature is constant in the PV diagram, like the midterm. Some people by mistake draw TV diagram. This is PV diagram. Temperature is constant like this. Along constant temperature line, the P decreases with V. Let's remember, PV equal RT. If temperature is constant, P inverse proportional with V. Boyle's law. Do you remember Boyle's law, guys? Or this is Charles. I think this is Boyle's law, yeah. Temperature is constant, okay? So P inverse proportional with V, always. In gases, I mean. So gases, pressure, if volume increases, pressure decreases. If you have this, whenever you expand, pressure drop. Volume and pressure inverse proportional. Expand, pressure drop. Compress, pressure build up. Volume decreases, pressure build up. Volume increases, pressure drop down. So from 1 to 2, the pressure decreases, but the volume increases. The volume here, 1 meter cube, 2 meter cubes. The same from 2 to 3, but 2 to 3 is called reversible adiabatic. Reversible adiabatic, we call it isentropic. This is called isentropic. Isentropic means the entropy is the same. We're going to discuss it next lecture. Isentropic, adiabatic, and adiabatic and reversible is called isentropic. We call it isentropic. So Carnot cycle said we have reversible isothermal expansion, reversible adiabatic expansion. 2 expansions. It means volume always increases. Volume always increases, increase. But the pressure drop from 1 to 2 to 3. This is isothermal, reversible. Everything is reversible. Everything is reversible. Reversible. The most ideal cycle ever, Carnot cycle. Everything is reversible. So reversible. Everything is reversible. The first one, isothermal. The second one, adiabatic. Adiabatic, there is no heat. Isothermal, adiabatic, isothermal, adiabatic, isothermal, adiabatic, isothermal, adiabatic, isothermal, adiabatic. This guy is isothermal, adiabatic, and reversible. We call it isentropic. We're going to discuss it in next lecture when we talk about entropy, chapter 7. Okay, guys? So far, so clear?
Yeah.
Okay. Remember, 1 and 2 has the same temperature. 2 and 3, they are not the same temperature, but 3 and 4, the same one. So 4, this is 3. When you go back to 4, it's compression. The volume decreases, pressure build up. This is called isothermal. So T3 equal T4. T1 equal T2. Correct? T1 equal T2. T3 equal T4 because this is isothermal. Isothermal. So the arrow going this way. Compression. How about 4 to 1? 4 to 1 is adiabatic. Adiabatic. Reversible adiabatic compression. So the pressure built up. Let me draw it for you, something a little bit more like this. So 1, 2, 3, and 4. Everything is reversible. Okay, guys? 1 to 2, isothermal. 1 to 2, isothermal. 3 to 4, isothermal also. So this is isothermal. This is isothermal. Okay, guys? Okay? Look at this one. This is the 2 temperature lines. So this is 1. This is 2. This is 3. This is 4. So T1 equal T2. Yeah, that's a horizontal line. T3 equal T4. Yeah, that's horizontal line. This is the Carnot cycle in the PV diagram, the Carnot cycle in the PV diagram and TV diagram. We discussed before. This area is the work done. Correct? This is the work done. You remember this, guys? This area is the work done. And also, this is the maximum work you can get. So let's say you want to obtain work from this. In reality, what happened? One does not go this way. It go a little bit lower. 2 to 3, a little bit bigger. So 3 to 4, a little bit larger. The same for here. So the area will be finally smaller. The area will be finally smaller. Every side decreases the area. So actually, if you want to go from here to there, non-isotropic, it's going to be like this. So the area will decrease. If you want to go here, area will decrease. If you go like this. So in the orange one, much smaller than the blue one. Inside the pink color, much smaller than the black color. Correct? Between the black color. Correct, guys? Correct?
Yeah.
So that this one, of course, smaller. And this is the good thing about Carnot. He said, I'm going to give you the maximum limit. You cannot go more than that. As long as your temperature is between these two temperatures, it's impossible. It's impossible to go beyond these black lines. So yours, in reality, is this one. Oh, wow. So we can go up to the maximum to the black lines, but we cannot go more than that. You're only inside, confined, trapped. So the maximum is the black line. But in reality, you are inside that. Inside that. There are a lot of things to talk about in this one. I described this in details in your lectures, in the PV diagram. We used to use this temperature, guys. We call it T high, TH, like U high. And we used to use this temperature, which is constant, T low, T high, and T low in the PV diagram and the PV diagram and TV diagram. The higher temperature, TH, the lower temperature is TL. So from 1 to 2, 1 to 2 is reversible isothermal expansion. Isothermal. Isothermal. What's isothermal, guys, means? Somebody tell me what isothermal is?
Temperature is constant.
Yeah.
T1 equal T2. Perfect. Adiabatic. There is no heat. Reverse. Everything is reversible. Isothermal, adiabatic. Isothermal, adiabatic. It's hard to remember this. Hi guys, it's hard to remember. Isothermal, adiabatic, isothermal, adiabatic. Don't say the exam is open. No, try to make your brain always think in thermodynamic way. So remember, this is isothermal, adiabatic, isothermal, adiabatic. Isothermal, adiabatic. Isothermal, adiabatic. Isothermal, adiabatic. This is called a cycle because I return back to original initial state. Isothermal, adiabatic. Isothermal, adiabatic. Isothermal, adiabatic. Adiabatic, everything is reversible. Adiabatic and reversible is called isentropic. We're going to discuss it later. Here also, reversible and adiabatic, also isentropic. So if you plot this, later in the TS diagram, it will be like this: 1 to 2, isothermal. 2 to 3, guys. How can I go from 2 to 3? Isentropic. Delta S is 0. There is no change in entropy. How can I go, guys? Can somebody tell me? Where is the constant entropy line from 2 to 3? I want the x-axis to be constant. Where? You need to move what? Vertically. So of course 3 is here, 4 is here. So this guy and this guy are isentropic. Guys, which one is easier? The PV or TV or TS? Which one is easier for you to remember? Which one is easier, guys? PV or TV or TS?
Probably TV.
How about the TS is a square, just a rectangle? Which one is easier, rectangle or kind of, I don't know, parallelogram or, I don't know, diamond? Which one is easier to remember? With the Tokyo,
TS then.
of course, TS, the rectangle. How about the rectangle? Which one is easier to draw? So that's why in the coming lectures, we're going to talk about entropy, because entropy is a very important physical property. Very important physical property. We wish to have 0 delta S. We wish. The reality is not. Does anyone have any question, guys? Anyone has any question, guys? Guys? Hello, hello?
Are we ever going to be required to plot all 3 of these, or are you just simplifying the graph?
Of course, you need to know everything. When I ask you in a problem, I'm going to give you an exam, hopefully by chapter 9 and 10, if we are alive in this pandemic. So if we are alive, you're gonna plot for me. I'm gonna explain for you. For example, let's say this way. I have a cycle. For 1 to 2 was isochoric. So you know, if you plot the PV diagram, you're gonna move vertically, upward or downward, up or down. The second one was, let's say, pressure was constant, isobaric. Entropy was constant, isentropic. Temperature was constant, isothermal. Adiabatic, Q is 0. Adiabatic is very similar to isentropic, very close, especially if it's reversible. If it's irreversible, it's be a little bit different. But the good news is you need to know how to draw anything. Constant entropy line, constant temperature line, pressure line. For now, you need only temperature, pressure, and volume. 3. We're gonna add entropy. So we have 4. You're gonna draw anything from these 4. Temperature, isothermal, volume, isochoric, pressure. So you need to know how to read the problem and draw it in PV, TV, TS. And we're gonna draw the whole steam table in terms of TS diagram. So we plotted for PV, we plotted for TS, TV. We're gonna draw it for the TS diagram. Very similar to what we did before. So the more you draw, the more you understand the physics to redraw it in a curve, it's better for you to use table. If you are in the very left, use compressed liquid. If you are in the middle, saturated mixture. If you are superheated, use table superheated. So you know from where the state is. You know from where the state is. Either from steam table or even ideal gas law. Okay, guys? We are done now. So hopefully, if you have any, do you have any question, guys? First.
Wouldn't the TV graph be wouldn't the curves be inverse of what they are right now?
One.
Yeah.
This one.
Yeah.
It's 1 to 2 arrows this way, 2 to 3 arrows downward. So
I'm
here,
saying those curves in between, because like the PV diagram isn't usually from as you increase volume, the pressure goes down, but with temperature, as you increase volume, the temperature goes up.
This is called isothermal expansion. Isothermal means what? 1 to 2.
Temperature is constant.
You said it. You said it. So it means horizontal. So 1 here, 2 is either left or right. Correct?
Yeah, I mean the lines under it though.
These two,
Like if
usually,
you would draw the regular
usually,
TV
yeah. So for 2 to 3, let's do this way. Look, PVT. Look, pressure and temperature are proportional to each other. Correct? For if the pressure increases, usually temperature increases. If the temperature increases, usually pressure increases. Correct?
Yeah.
That's usually. It means if V is constant, for example, P, of course, proportional to T. I think this is Charlie law. P always, in terms of gas, P proportional to T, if volume is constant. So typically, if temperature increases, pressure increases. If you get a gas and you compress it, what will happen? It get warm and it get high pressure, correct?
Mm-hmm.
So usually think this way. Okay? So here pressure drop, temperature drop. Here pressure build up, temperature build up. Okay?
Okay.
Make sense?
Yeah.
So usually think of this way. Only pressure and volume, inverse proportional. But actually temperature with volume, inverse proportional, direct proportional. Temperature with pressure, also direct proportional. Okay? But
Alright.
usually pressure is strongly proportional to temperature. If you have a gas balloon and you compress it, it's getting warmer, the gas inside. And pressure is built up, correct? And volume drop.
Yeah.
Okay, guys? Make sense?
Yeah.
So here is isothermal is so clear. The isothermal is so clear. This one kind of vague, but you know the physics. The physics says pressure build up, temperature build up. Pressure drop down. But this line, constant temperature, don't confuse. This kind of reduction or decrease between P and V, not temperature. The temperature is constant here. Make sense? So remember, if you remember when I started to talk, I said, when I move along constant temperature line, forget about temperature. Think about pressure and volume. The pressure and volume decreasing proportion, inverse proportional to each other. Forget about temperature, because temperature is constant. Do you remember this, guys?
Yeah.
We are over now, guys. Have any question, guys?